In this tutorial, we're going to talk about section 3.1, which is about extrema on an interval. So we're going to look at the minimums and the maximums within a certain interval of x values of functions. And there's a lot of vocabulary, there's a lot of definitions in this section, and we need to pay really close attention to them. So let's look at the first part of this. Okay, so let's take a look at this. This is on page 164 in your textbook, and it talks about the definition of what extrema mean. In the first part of it, if you can read, it says, let f be defined on an interval I. So that could represent anything, and it has to contain the point C. So the first part of this that we really have to understand is that f has to be defined. That means that it can't be an open circle, it can't be an asymptote. None of those things can happen. Now, the very next thing says, number 1, f of c, the point that we're interested in, is a minimum of f on that interval if f of c is less than or equal to f of x for all x and I. Okay, so that's a lot of information. What does it mean? So let's take a look at this picture. And this is also on page 164. But let's say that C, the point that we're interested in, is this guy right here in blue. Okay, so the number 1 first says that it has to be defined, which it is. It has a closed circle, it has a value. So in other words, C is going to be equal to 0 in this particular case. And it is defined. So number 1 says that f of c, in other words, f of 0, is less than or equal to any other x value that I plug in here for every single x value in that interval. Now if you look here, the interval only goes from -1 to +2. So within that interval, all of the other values of x that I plug in are always going to be bigger than this value here at c equals 0. So this is what we call a minimum. Now the next part says, number 2, f of c is a maximum of f on that same interval if f of c is greater than or equal to all of the other f of x values for all x in that interval. So in this particular picture, my number 1 guess would be this guy all the way up here at, what would that be, c equals 2. And first of all, it is defined, so I can use it. And I can have value here as well because this interval includes 2. If you look down here where it says the interval, do you see how it includes 2 there? So we can use this. And f of 2, if I were to use this, should be greater than or equal to any other value of x that I put in there. And that is a true statement. So this is what we call a maximum. So these are all very key points to these definitions. Now there's one other thing that we need to make sure that we read in this definition, so let's take a look at that. And that is that it says the minimum and maximum of a function on an interval are the extreme values or extrema. And you can have more than one. You can have several maximums and minimums. So the minimum and maximum of a function, and I'm right here, right now in green, the minimum and maximum of a function on an interval are also called absolute minimum and absolute maximum on that interval. And so in order to be a maximum or a minimum, like in absolute terms, it must be the very biggest or the very smallest. All right, so let's take a look at some more definitions. So now we need to talk about what relative extrema are versus absolute. So this is on page 165, and number 1 says if there is an open interval, that means that there's parentheses on both ends, containing c, okay, a point that we're interested in, on which f of c is a maximum, then that point is called a relative maximum of f. Or you can say that it has a relative maximum at that notation. And then the same thing goes for a minimum, and that just means that it's relative because it's only relative within that interval. It's not the absolute minimum of the entire function. So, for instance, in this particular picture, we have, this is on the same page, we have this function, f of x equals x cubed minus 3x squared. And it's trying to highlight this point here, and that does not show up at all. Let's use green. This point here and this point here. And first of all, we want to make sure that they are defined, which they are. So at the bottom it says f has a relative maximum at 0, 0, and a relative minimum at 2, negative 4. And we know this because we're just looking at an open interval, and as you can see, there is no set interval. It's not closed. So we assume that this function is just going on. We're just trying to find the maximums and minimums throughout this entire function. So because this is a maximum point here, we call it a relative maximum, but I know that this function, if I were to continue drawing it, there's a part of this function that just keeps on going up and up and up forever and ever and ever. But because of the definition of maximum, this is called a relative maximum. It's relative to this area, okay? It's like what they call a hill, okay? But it's not the absolute maximum this function is going to go. And the same concept goes with minimum. If I were to continue to draw this function downwards like this, it would keep going forever. But in terms of relativeness of the zoomed in part of this function, this would be considered a relative minimum. So I want to take a look at these three pictures. We have, this is number 1, this is number 2, and then this is number 3. Because something very interesting happens when we talk about relative maximum and minimums with respect to derivatives. So in number 1, when I look at the relative maximum they already have laid out, try to see if you can find what the tangent line of this function would look like at that point. And I'm just going to sketch it in here because it's not so clear to see, but it should be a horizontal line. In other words, the slope of c that I'm interested in is equal to 0. On number 2, this is an absolute value function, and although this has a cusp or a sharp point, it's still considered to be a minimum because it fits the definition. However, in this one, if you look at the bottom, the derivative does not exist because it is a sharp point. But there's something very interesting about that as well. And that is that simply, it doesn't seem like because the derivative doesn't exist that it should be considered a relative maximum or minimum, but it is. So that's something to keep in mind. So cusps can be maximums and minimums too. And then in picture number 3, we have f of x equals sine x, and we know that to be a sinusoidal function. And within this particular picture, when I take a look at where the relative maximum is, if I were to make my tangent line, once again I get a derivative of 0. F prime of c is equal to 0. The same thing happens at the minimum. If I were to draw a tangent line here, purple may not have been the best color to use here, f prime of c is also 0. So maybe we can make some kind of conjecture here. And that is that maximums and minimums occur when the derivative is 0. And not necessarily every single time, but most times it does. And the only case I'm taking into consideration is in number 2, when we have a cusp, or perhaps it's an asymptote or something funky like that. But everything else, it does work. So the next thing that we want to talk about are critical numbers. And the reason why we go right into critical numbers is because look at the second part of this. First, f has to be defined at c. So we're getting pretty used to that being in our definitions. We really can't talk about any point of c unless it's defined. But then it goes into say, if f prime of c equals 0. Well, that's very interesting since that's what we just made a conjecture about. Or if f is not differentiable at c, in other words, like a cusp, then c is a critical number of f. So let's take a look at a couple pictures. So in the picture down here to the left, we'll call it number 1. And actually, I'm going to stop using colors. I think black is going to be the best. There we go. 1 and 2. So this particular picture, C, the point that we're talking about, which is right here, okay, it is defined, but f prime of c is not equal to 0 because this is a cusp. So it's not differentiable at c. So it's still a critical number, though, because of this definition. And on number 2, this is another instance. So at c, once again, f is defined at that point, and f prime of c is equal to 0. In other words, the slope is equal to 0. Okay, there's my tangent line. So this is also considered to be a critical number. And we have a theorem in our textbooks, also on this very same page, that says that if f has a relative maximum or minimum at this point, then it's automatically a critical number. So if you have a maximum or minimum anywhere, it's considered to be a critical number, period. So from here on out, if we want to find extrema and we have a closed interval, these are some guidelines to follow. So we're going to go through these guidelines by looking at an example, and we're going to specifically look at example number 2 in your textbooks, and it basically says find the extrema of this function, f of x equals 3x to the 4th minus 4x cubed, and my interval is between -1 and 2. Okay. So let's take a look at number 1. First of all, it says, find the critical numbers of f in the interval. But we don't want to include -1 or 2 because of this notation. So in other words, I want everything up to -1 and everything up to 2 non-inclusive. So the first thing that we want to do is, in order to find the critical numbers, that's where my derivative is equal to 0. So let's first of all go ahead and determine the derivative of this function. So f prime of x would be equal to 12x cubed minus 12x squared. So in order to see what our values are, our critical numbers, we want to set this equal to 0. So 12x cubed minus 12x squared equals 0. So let's factor out anything that they have in common. They both have a 12 and they both have an x. So 12x times x squared minus 1 equals 0. So I set each of these parts equal to 0, just like in factoring from way back in the day. 12x equals 0, and then x squared minus 1 equals 0. So in the first case here, in order for this to be true, I have one solution, that would be x equals 0. And in the other one, which I'm not sure why I put a squared there, let's go ahead and get rid of that. I'm sorry, I'm tired. I did not see that. This is just an x. Sorry about that. So if I were to add 1 to both sides, I get x equals 1. So these are my critical numbers. So that means at these points, there's either a maximum or a minimum occurring somewhere. So number 2 then says, I'm going to work at number 2 over here, evaluate f at each critical number in A, B. Now note that this does not say f prime. I'm working with my original function. So I'm going to do f of 0, which would be 3 times 0 to the 4th power minus 4 times 0 cubed, which of course equals 0. And the next one I want to look at is f of 1. So 3 of 1 to the 4th power minus 4 times 1 cubed. So this all comes out to be -1. Okay, so the first 2 steps are done. And now number 3 says evaluate f at each endpoint. So, and all the work for this is in your textbook, but I'm going to just go ahead and tell you that f of -1 is 7, and f of 2 is 16. And that comes from my interval up here where I first started my problem. The -1 is right here, and the 2 is right here. That's where those numbers came from. Okay, so I'm going to make sure that I highlight all of these values here. So f of 0 was this guy right here. This is f of 0. This guy right here is f of 1. And then I have f of -1 is 7, and f of 2 is 16. Now, step number 4 says that the least of these values is the minimum. And that would be f of 1 right here. So that means 1 is my minimum. So this guy right here, oh, not that one. Once again, I'm sorry, I'm tired. This guy right here is my minimum. And my maximum would be f of 2 because it has the biggest value. And these are considered to be your critical numbers and your maximums and minimums. But note that this does not mean that they are relative, nor does it mean that they're absolute, because we are on a defined interval and we're not looking at the whole picture. So that's how you can use your new information to help you find this really key information about your functions and derivatives. And that's going to conclude this tutorial.